Hi everyone. First, I would like to thank my co-authors and teammates for all their work and effort. Also, I would like to thank Tom Spiro and Professor Andrew Kang for putting together this special session. Today, I'll present our paper, which is about bridging academic open-source EDA to real-world usability. This work has been driven by the University of Michigan and UCSD, and is supported in part by the DARPA IDEA program as part of the OpenROAD project. We all know that ASIC design is difficult, expensive, and risky. Tools have thousands of command option combinations. They are complicated and unpredictable, so you need expert users. This brings cost and risk and cripples innovation. We see pictures like these. On the left is the problematic raised by DARPA in Andreas Olofsson's talk, where we can see that the cost of silicon is under control. The cost of designing in silicon is out of control. The histogram on the right is extracted from the Synopsys Analyst Day talk. The cost for companies to design a 5 nanometer chip is likely to be 100% larger than the cost to design a 7 nanometer chip, while cost to design a 7 nanometer chip is 35% higher than the 10 nanometer chip design, and so on. This cost explosion is mainly driven by the increase of features from a node to another, especially in the IoT design space, where more connectivity and higher volumes of data are necessary. So this leads to extremely complex design processes. Manual design effort, which is still required at different stages of the design flow, such as SoC architecture, planning, analog design, and IP qualification, is considered as one of the key contributors to these costs. Multiple efforts are focused on automating these steps, especially analog design, which remains a major roadblocker to a full-stack silicon compiler. Another major hurdle that requires attention are proprietary tools licenses. And so in conclusion, tools have become highly complex, and cutting-edge place and route flow requires an extensive number of commands and options. Such trend is due to the increasingly intricate design rules. This growing complexity dramatically impacts release schedule, which can be disastrous and adds to the risk in hardware design. So innovators have a hard time innovating, doing design ideation and design exploration in hardware. When we talk about the design crisis, we really mean that access to silicon is out of the reach of designers. So how do you change hardware design so that it is less difficult, needs fewer experts, and costs less? The obvious answer is a combination of automation and intelligence with self-driving design tools and flows, and then there is open source. In 2018, DARPA launched the IDEA program as part of the US Electronics Resurgence Initiative. The IDEA program aims for hardware compilers 2.0, no humans, 24-hour turnaround time, eventually with zero loss of quality. This shifts the focus from tools that enable experts users to achieve the ultimate PPA to self-driving tools that don't require experts or time to tape out a working chip, and leading to democratization of hardware design. So who are the design advisors? In the case of OpenROAD, originally we proposed to develop the whole thing with PhD students and postdocs at 4 universities. Separately, students and postdocs at a 5th university would serve in an internal design advisor's role, such as users, product engineers, and AEs all rolled together. We built in this separation to ensure that when commercial tools are used to report metrics to DARPA, the students who write the tools aren't the ones doing this. So that was the initial vision. The internal advisors are in charge of the flow, PPA assessment, and calibration data, while developers are in charge of the tools. I would say a key lesson learned is that open source EDA goes beyond academic research skill sets. Over time and changing needs, the separation became less obvious as we noticed tools being developed by design advisors to address the finishing steps or antenna rule checkers, for example, and vice versa. In fact, very soon we knew we needed a dedicated, experienced EDA architect and technical manager from outside the team. And the OpenROAD project, led by Professor Andrew Kang, figured out how to make this happen. Tom Spiro, shown on the left, has been OpenROAD's chief architect since July of last year with multiple other industry veterans who share the vision of open source EDA. So now let's have a look at the not so long history of OpenROAD and the evolution of the flow since this project was launched. A year ago, OpenROAD showed the proof of capability being automatic generation of design rule clean layout in 65. The alpha release of OpenROAD used separate binaries for each tool and relied on a patchwork of configuration files and command line arguments to run each tool in a similar way to the 1980s EDA flows. It is important to note that a lot of these binaries have been developed previously, such as HYOSYS from Clifford, or physical design tools that originated either from Prof. Andrew Kang research group or from other co-PIs and project consultants. The internal advisors worked closely with the developers to mitigate all the interfaces mismatches between tools. In fact, these tools varied in maturity and some of the place and route steps were not available. Our tool performs the RTL to GDS chip implementation flow, starting with logic synthesis and ending with the GDS2 tape-out database. Early this year, during the integration exercise, we have released our first version of our tool using a modern integrated architecture. The largest improvement to OpenROAD-flow was the shift from a file-based interface to a unified database interface. Once the tools were integrated into the unified app, all interfaces were also unified into a single binary with a TCL interface for the users. Then the OpenROAD-flow has expanded its support to include 14 nanometer FinFET and the newly open sourced Skywater 130 nanometer. In addition, open source DRC and LBS are available through KLayout. As shown in this diagram, in addition to adding more flow stages, another key element is to simplify the user's flow interactions. To do so, the important data preparation step is used to minimize the number of user adjustments needed to set up a commercial PDK such that it is usable by OpenROAD-flow. Optimization, while not explicitly shown here, is embedded in the placement and CTS stages. I also would like to highlight that this work is driven by the internal advisors, who consists of a handful of PhD students and researchers, and cannot be compared in any way to the legions of engineers at commercial EDA houses. The OpenROAD project has been following a very aggressive timeline, summarized in the following figure. In mid-July, we achieved an automated totally clean result, by which I mean DRC, LBS, antenna, all clean in caliber, for a single core version of the University of Washington Black Parrot SoC. This was implemented in GF12 IP using ARM 9-track cells, ARM SRAMs, and NVCAS IOs in the same 3x3mm package design that the Black Parrot team had used for their original GF12 tape-out. The OpenROAD team is already tackling the QoR to improving the timing engine of the OpenROAD app, and multiple features are under development in addition to new process nodes support. Developing and maintaining the OpenROAD flow has led to several challenges along the way to meeting OpenROAD's development schedule goals, And in the next slide, I'll go through the main gaps and issues that we have faced. The continuous integration infrastructure has been introduced to the OpenROAD project to help ensure integrity and quality of the code base. In this diagram, you can see the three key branches, a tool develop branch, and the staging branch, and the master branch. The develop branch maintains day-to-day development activities. It runs unit tests and tool regression tests, and all contributions in the form of a PR or pull request are issued to develop. Changes merged to the OpenROAD branch are tested against the end-to-end flow. Repo owners initiate this merge to ensure that tools still run within OpenROAD-flow. Finally, the master branch holds a stable release to the code base. This methodology allows asynchronous updates to the tool's submodules and ensure stable versions to be merged to the master branch. Another challenge faced by the design advisors is what we call tool workarounds. As illustrated in the figure on the right, in cases where the root issue resides between tools, the design advisors would often be able to perform external processing as a workaround for lack of tool support. This allowed developers to focus on more critical issues. Some previous examples include fixing inconsistent depth output between tools, fixing technology-independent tool issues, and adding partial support for yet-to-be-supported file formats, and for example, interconnect parasitics. To address this, we needed a flow able to pass designs through all available steps provided by the development team. This included the ability to skip or work around flow steps as necessary, and therefore the earliest iteration of our flow leveraged commercial tools to generate clean artifacts, such as devs, floor plans, route guides, etc. It is important to note that several of these workarounds have enabled the development team to hit our schedule for 14 nanometer node support, but now underlying issues must be thoroughly investigated to reduce the induced technical debt. The OpenROAD-flow's vocation is to be a highly automated flow. It is thus important to identify design intent and constraint early on in the flow stage and translate that into relevant decisions. To achieve this vision, the design advisors and developers are working closely to automate much of this process and build the intelligence able to select and tune design parameters such as design area and utilization, cell placement, and global routing settings. The last challenge I would like to mention in this talk is related to routing. Detailed routing for FinFET technology nodes is a significant challenge. A routing tool must understand all the hundreds of complex design rules in order to properly route designs without violations. As internal design advisors, helping Triton Route to achieve zero DRVs with limited time and resources was a significant challenge. Following the generic node enablement methodology, we made and enforced assumptions in routing rules to minimize the required design rule support. Another aspect to general node enablement is the handling of macro cells. And for that, we adopted a wrapper over the SRAMs cells to align pins to the routing tracks. For example, as shown in the figure on the right, the route SRAM has extra space near the pins and extended to have an on-grid location. The area overhead is less than 1.5%. Also, to be able to test the OpenROAD tools properly, real-world design test cases are needed. The original intent of the design advisors was to create a suite of test cases based on the previous tapeouts of real designs. We quickly ran into several issues that prevented us from creating meaningful test cases for the developers. And in fact, a modern SoC would be composed of multiple cores, analog and mixed signals IPs, interfaces, and other design components depending on the application. This often means diverse and dense floor plans, multiple voltage and power domains, multiple clocks, and sometimes circuits level schemes. To address this, we stripped down the test cases to accommodate the tool capabilities and meet the project milestones and specific features we needed to evaluate. As illustrated here, timing constraint files were simplified to address a single clock domain with no support to partitioning, a single voltage domain, and a fairly acceptable range of SRAMs macros going up to 100 cells. Timing based on a single clock is possible. However, analog design isn't handled yet in the flow, such as handling power intent files. Finally, OpenROAD-flow provides full chip designs with I/O rings, enabling developers to test tools at the SoC level rather than only at the block level. Proprietary CPUs and IPs oriented the design advisors towards open source designs such as RISC-V cores. It is important to maximize shareability, and thus commercial IPs were removed as well. In fact, as the tools matures, we are progressively tightening design constraints and adding more features and test cases from the open source community. Here you can see a summary of the design suite within the OpenROAD repo. On the left are test cases implemented in 65 and GF14 using our flow. And in the second row, we can see the Black Parrot with 2 cores and the Swerve design with macros in GF12 IP. Continuous integration is commonly accepted as a game changer that allows to pinpoint broken code changes. It has been applied to many fields, and the EDA tooling is benefiting in its turn from such infrastructure. This is another area which was not clearly enumerated in the original project task structure. By introducing the CI, it is possible to build and test the tools individually, and if successful, it tests the new code changes within the OpenROAD flow. This ensures that the OpenROAD unified build environment isn't compromised by the code changes. Back to our roadmap, in mid-July, we achieved an automated DRV clean result of the Black Parrot design, which is a great milestone, but what comes next? Timing. PPA analysis has been an important part of our work. Thus, we have spent a considerable effort looking into our timing reports, tweaking hold and setup constraints to meet a reasonable sign-off target. And so this is where we are today. The integrated app OpenROAD is in blue and is tightly tied into the timer and the DB. Most of our tools are integrated today and are sitting in a mono repo. This trend of consolidating repos and not using submodules is accelerating in our project. There are 3 other executables in the flow, YOSYS for synthesis, Triton route for detail routing, and K-layout for layout, finishing, and GDS merge. As mentioned earlier in my talk, full autonomy of the flow isn't an easy task and is expected to happen gradually as the flow matures. As a short-term goal, we aim to improve the user experience and make it more intuitive. Both the novice and expert user should be able to run a design through with a minimal design effort. Documentation and improving the tool errors, reports, and warnings should make the flow issues resolution more fluid and highly effective. As a reminder, our mission is to achieve a 24-hour no human RTL to GDS in advanced foundry nodes, while catalyzing an open source ecosystem for researchers, tool developers, and users. Keeping this in mind, our philosophy is to make the flow autonomy central to any new development. or enhancement. QRR, although coming as a secondary, is expected to be improving over time, and the shortcomings such as loosen up timing are being addressed as we speak. Automatic correlation as well as new features are on our radar. Design techniques such as automatic clock gating, multi-voltage, or partitioning are being investigated as we speak, along with parasitic extraction tools such as OpenRCX. So that's for the future. And by this, I end my talk and invite you to read our paper for more details. Thank you.